Catalytic hydrogenation. Just as alkenes, alkynes can be reduced by catalytic hydrogenation. The initial product of hydrogenation is an alkene, but it is often difficult to stop at this stage because hydrogen has got a strong tendency to add to alkenes in the presence of these efficient metal catalysts, and therefore the product is going to be an alkane. However, the reaction can be stopped at the alkene stage if a poison metal catalyst such as Lindlar's catalyst is being used. Lindlar's catalyst is prepared by precipitating palladium on calcium carbonate and treating it with lead acetate and quinoline. And this catalytic hydrogenation using Lindlar's catalyst is going to follow the syn addition, where the two hydrogens that are going to get added to the triple bond are going to be exactly in the same side of the alkene molecule. Why syn addition? Because the alkyl molecule sits on the surface of the metal catalyst. And you can see that this is your metal catalyst where the hydrogens are adsorbed. And as the alkyl molecule approaches this metal catalyst, the two hydrogens that will be delivered, they are going to be in the same side of the alkyne molecule. And therefore, it's going to follow this syn addition. When you want to convert an internal alkyne into trans alkene, then you have to use either sodium or lithium in liquid ammonia. And in this case, the reaction is going to stop at the alkene stage because sodium or lithium is going to react more rapidly with triple bonds than it would react with double bond. And this reaction is called a dissolving metal reduction reaction. Ammonia is a gas at room temperature, and therefore it has been kept in liquid state by cooling with liquid nitrogen. And here is a picture of sodium dissolving in liquid ammonia to form a deep blue solution. Let's now draw the mechanism for the formation of a trans alkene in dissolving metal reduction reaction. First, to begin with, the single electron from the s orbital of sodium is transferred onto an sp carbon of the alkyne. So basically, one of the pi bonds in the alkyne is going to break, and it's going to lead to the formation of a radical anion. This is called as a radical anion because you have a radical, which is basically a free electron, right? And also you have a negative charge on this carbon. This is more like a carbanion. So this is called as radical anion. And this radical anion can exist in the cis configuration or in the trans configuration, but the equilibrium will always favor the trans isomer. And this radical anion is a strong base, and it will abstract one of the hydrogens from ammonia. So these electrons will go and abstract this hydrogen and thrust these electrons onto nitrogen. When it does so, it's going to form a vinylic radical. So this is a vinylic radical. So this one right here is a vinyl group, right? Vinyl carbon. And on the vinyl carbon, we do have a free electron. So therefore, this is going to be a vinylic radical. And in the next step, again, another single electron transfer from sodium to vinyl radical happens, leading to the formation of a vinylic anion. So you will have one more sodium atom, which is able to donate that electron to form the vinylic anion. So this is a vinylic anion. And since the vinylic anion is also a strong base, it will go and abstract one of the hydrogens from ammonia to form the trans alkene. The final product would be a trans alkene. And you can see that the two hydrogens are on opposite side. Why do we get trans alkene as a product in this reaction? So let's take a look into these different intermediates. So this is a radical anion, one of the intermediates which is obtained in this reaction. And this is a vinylic anion. This is radical anion because you have a radical and also a negative charge on this carbon. And similarly, this one is a vinylic anion because you have a negative charge on the carbon, which has a double bond, right? So both of these intermediates have the ability to exist in cis and as well as trans configuration. So on the radical anion, this is a trans isomer and this one is a cis isomer. So why this one is a trans isomer? Because the two methyl group are on opposite side. This one is a cis because the two methyl groups are on the same side of the molecule. And although the trans isomer and as well as the cis isomer are formed, the equilibrium will always favor the formation of the trans isomer. Okay, here again in the vinylic anion, this is our trans isomer and this one is a cis isomer. And in the cis isomer, since the two methyl groups are closer to each other, there is going to be electronic repulsions between those two methyl substituents, right? Because of which the trans isomer is going to be favored, and therefore this is going to lead to the formation of the trans alkene.